Hi, today we will learn about how to prove by using the principle of mathematical induction and how to find the solution sets of the inequality. Okay, let's begin. To apply this principle, there are 3 steps. Number 1, prove that the statement holds for n equal to 1. Number 2, assume that the statement holds for n equal to k. No need to prove. Number 3, use number 2 to show that the statement also holds for n equal to k plus 1 for any positive integer n. Let's see the questions. Now we want to know either this statement is holds for any positive integer n. So we let P be the statement of n. First step, we need to show that the statement holds for n equal to 1. We substitute n equal to 1 into the statement. We easily get 1 equal to 1. Therefore, the statement is true for n equal to 1. Second step, in this step, we just assume without proving that the statement holds for n equal to k. We substitute n equal to k into the statement. Thus, we assume the statement is true for any positive integer. Third step, we need to show that the statement also holds for n equal to k plus 1 for any positive integer. So we start with the left side and I use the induction hypothesis to obtain the right side. We substitute n equal to k plus 1 into the statement. From second step, we already assume that the statement holds for n equal to k. So we get k multiplied 2k minus 1 plus 4 multiplied k plus 1 minus 3. We expand the bracket to get 2k squared plus 3k plus 1. In the form as the statement P of n, we factorize to get k plus 1 multiplied with 2 in the bracket k plus 1 minus 1. Therefore, the statement n equal to k plus 1 is true. Thus, the statement P of n holds for any positive integer. Next question is about the inequality. Given that the absolute value of modulus x minus 3 plus modulus x plus 2 less than or equal to 11. Just for a reminder, we can define the absolute value as piecewise form. First step, we need to form the piecewise. When modulus x minus 3 equal to positive form if x bigger than or equal to 3 and negative form if x less than 3, and for modulus x plus 2 equal to positive form if x bigger than or equal to negative 2 and negative form if x less than negative 2. Second step, we divided the cases by using number line. When x less than negative 2, we have negative x plus 2 and negative x minus 3. When x in between negative 2 and 3, we have x plus 2 and negative x minus 3. And when x bigger than 3, we have x minus 3 and x plus 2. Third step, for first case, when x less than negative 2, we have negative form of x minus 3 and x plus 2 less than or equal to 11. We simplify the inequality until we have x as the subject. So we get x bigger than or equal to negative 5. Then we find the intersection between x less than negative 2 and x bigger than or equal to negative 5 by using number line. Thus, we get x in between negative 5 and negative 2 including negative 5. For second case, when x in between negative 2 and 3 including negative 2, we have negative form x minus 3 and positive form x plus 2 less than or equal to 11. We simplify the inequality until we have x as the subject. However, we get 5 less than or equal to 11. Noted that it is always since 5 less than or equal to 11 is always true, thus the intersection between both inequality x will be in between negative 2 and 3 including negative 2. For case 3, when x bigger than or equal to 3, we have positive form of x minus 3 and x plus 2 less than or equal to 11. We simplify the inequality until we have x as the subject. So we get x less than or equal to 6. Then, we find the intersection between x bigger than or equal to 3 and x less than or equal to 6 by using number line. Thus, we get x in between 3 and 6 including 3 and 6 itself. Next step, we need to find the union of the three cases. we represent the case into number line. Thus, the solution sets of this inequality is wholes from -5 to 6, including both -5 and 6. Okay, bye. Thank you for watching this video.